Okay, so Jahid, part of our effort to our research, and not only for the CENJOWS setup, so to the organizing world also. Uh, we listen to the Tiwari, who has been counsel of us and part of multi activities, is going to speak on a very current contemporary topic. So, it may appear little technical in nature. This is something which is required by each one of us in a big way. So, without wasting much time, I'll request Prakhar to introduce the speaker for the benefit of all our listeners, and thereafter Deepak to commence his talk.
So, our today's speaker, Mr. Deepak Tiwari, is a technical research assistant and assistant public relations officer at CENJOWS. He is pursuing his doctoral research from School of National Security Studies, Central University of Gujarat, specializing in the strategic implications of emerging and disruptive technologies in India's military domain. With a multidisciplinary background, combining BTech in mechanical engineering with MA in defense and strategic studies, he strives to cover both the horizontal and verticals of technological implications on national security policy. Also, affiliated with the Center for Joint Warfare Studies CENJOWS as a subject matter expert, Deepak focuses on hypersonic weapons, quantum technologies, and AI-enabled systems. He has completed 3 faculty development programs on quantum technologies, communication, and sensing from a faculty development program organized by MNIT Jaipur, IIT Kanpur, and IIT Roorkee, funded by MIT and endorsed by Department of Science and Technology, National Quantum Mission, AICT, and UGC. Deepak's research experience includes serving as a research intern with IISc Bangalore and University of Amsterdam and research assistant at an ICC SSR funded major project on contemporary and future force structure in India's internal security operations. Researcher with Atal Bihari Vajpayee Institute of Policy Research and International Studies. He has published journal articles, books, chapters, and book reviews, issue briefs, and web articles with reputed journals and think tanks, and has presented paper in many national and international conferences. Over to you.
Thank you, Prakhar. I'd like to convey my sincere thanks to Director General CENJOWS for giving me this opportunity to talk in this very interesting topic. So, starting with the basic. So we all know the technology has remained a strategic enabler of war since the beginning. But as I read in a book, Future of War by Lawrence Friedman, what he calls technology now is a cognitive disabler of peace. Quite interesting to hear, but what he meant is that these new platforms and domains now that technology has provided, like cyber and space, are now places where war is going on as we speak. These technologies are, providing a false sense of peace to us. Meanwhile, trying to find the vulnerabilities of states, people, and the critical infrastructure as we speak. Which is also the basically the oldest trick in the book, to deceive and then to defeat. But what I am looking to cover with this lecture is not just the geopolitical aspect of quantum technology, but also the basics of the technology itself. Because it's only when you have the knowledge of the technology can you dive deep into the potential in leading the coming paradigm shift. Most importantly, my objective is to make you all quantum aware, quantum literate, as and well versed with the terminologies of quantum technologies. Since we are going to have these discussion being in this think tank where we talk about technology and policies much often, we need to know the terms so that when we can, when we get into a debate and discourse, we can put our point with the confidence. The term that I used now, paradigm shift. So this term was first coined by Thomas Kuhn in his book, The Scientific Structure of Scientific Revolution. It was a first unique theory which explained how science evolves. So he says that science evolves in a cyclic process of normal science and evolutionary science. So there is a normal incremental development. Then there are revolutionary ideas by some great thinkers, and then the paradigm shift come, and we enters into a new paradigm. So like earlier in the natural science age, we had Aristotelian ideas, which is called natural physics, where we had just the logical understanding of our surrounding. It was not enough. As the human understanding grew, uh, Newton came, he gave the ideas, and then there was a paradigm shift, and we entered into what we call as classical physics or Newtonian physics. Uh, at the end of 19th century, this classical physics started to encounter anomalies as in glitches, some phenomena we could not explain with the classical physics. And then there was a crisis in the system, and then there was a new paradigm shift that led us to the quantum physics. Similarly, the same kind of paradigm shifts happen in the technology as well. For example, computers. Earlier, we used to have mechanical computers with gears and clutches, vacuum tubes. And then there was semiconductors, invention of semiconductors. And then we entered into classical computers, what we call modern computer as well, which are based on microprocessor, advanced chips, which are all based on semiconductors. Then slowly, as we will see in the next slide, these chips, as we trying to fit more and more transistor in a single chip, the size of the chips is being decreased. The new phenomena, the new problems are emerging, and now we are slowly, right now, at the paradigm shift. We are at the stage of the shift to enter into the quantum technologies, which is now at the foundational stage of development, and will soon, in 5 to 10 years, we'll see some groundbreaking quantum computers with quantum advantage and supremacy, something we'll talk about later. But all these two paradigm shifts in physics and the technologies are now leading us towards the quantum age. So later in this lecture, I'll talk about the technology, how this principles of and physics of the quantum mechanics works, and it leads towards technology. So don't need to be confused, because Richard P. Feynman, the father of quantum computers, he says that if you think you understand quantum mechanics, you don't understand quantum mechanics. The grandfather of quantum technology, Niels Bohr, he says if you are confused by quantum mechanics, you are not confused by quantum mechanics. That means you haven't really understood it. So there's nothing to worry about. It's that kind of a subject. It's very counterintuitive, and you can't imagine and understand with the surrounding. It's properly mathematics turned into machines, and then machines trying to figure it out how to work through mathematics only. So Moore's law, it's a very famous law. We have heard about it from some 20, 30 years. It says that in about 2 years, the size of microchips shrinks. You know, the number of transistors in a microchips doubles every 2 years, and they have tried to chart this complete development since 1950s till the recent. So we can see the graph here. Transistor approximately double in every 2 years. In 2022, Apple launched this Apple M2 chip. Actually, this one M1, M2 chip, which had 18 billion transistors in a single chip. So as we are trying to fit in a single size of chip more transistor, we are going deep into the material, and now we are at the molecular level. And when we go deeper into that, we go into atomic level. And this stage, the normal physics, classical physics starts to fail. It doesn't work. So we talk about this chip war, that we need smaller nanometer chips, but actually we are hitting the boundary. We are very soon to hit the boundary where there won't be smaller chips anymore. We'll have to shift. So the quantum computer, it's inevitable. It's a law of nature coming to in the form of technological evolution. So few problems, the characteristics and the few problems with the classical computers which leads up to this evolution is, for example, determinism. Normal classical computers, they when you put 0101 bits, they give a fixed output. No matter how many times you put 0101, there the output will be fixed. It's deterministic. Again, the classical computer execute operation step by step. You have to finish. See, there are protocol first job, first, then shortest job first. These are the protocol that computers use to basically perform actions because they can do one thing at a time. They are not multitaskers. Again, as we all know, the classical computers represents data in 0, 1 binary digits. Now, despite their power, we have supercomputers, very powerful computers nowadays, able to do lots of calculation. Despite that, we have evolved with our needs, with our data so much that these computers are not enough. Even the most powerful computer struggles to decode, this script and accurately predict the weather, for example, with the dynamic data, a huge quantity of dynamic data. So the major complexities are these four: time complexity, some problems, for example, when we have a large number of data on a single problem, and then the condition to analyze the data is dynamic. For example, there's a shipping company who has thousands of ships and they want to deliver their content in the most fuel efficient manner. Now you have to figure out the geopolitical condition in the routes, weather condition, there's piracy and lots of things. And through all these dynamic and fixed variables, you have to find the optimum solution. This is a very complex problem that the normal computers are unable to do. They give you the best approximation, but not the absolute, the correct solution that you can employ. There is space complexity. There is a limited number of space. For example, the memory we use to 20 GB, 100 TB, the disk we use. There's a limitation of that on every system. For example, we drink coffee. The molecule of the coffee is caffeine. The structure of caffeine, if you try to put in a simulate in a classical computer, the total energies of that molecule would take the and memories of the all entire computers combined on Earth. All the memories of the available computers or supercomputers in the entire world, if you combine them, you won't be able to simulate that single molecule. So that is the limitation. Now we are trying to go deeper into the molecular structure and try to understand how they behave in a different environments. Reversibility and energy loss. Heating problem, we understand that there's a Landauer principle which properly explains how even if you delete something from your computer, there's a loss of energy. Every single action that we perform on a classical computer, there's a loss of energy. It turns into heat, and that when we have data centers, this heating problem becomes a major issue. The last one is inability to model quantum system. How this problem came is, as we trying to go deeper into the classical mechanism, the molecular to atomic structure, trying to figure out how a drug delivery should be proper, how the material should be better suited to our needs. We are getting into these problems that we can't simulate how they will behave on computer, so that we can try in the physical real domain. So we need to simulate these quantum mechanical properties of matter, but we can't do it on a classical computer. So we need something different type of computer which follows this quantum nature. Now, enough for the classical computers. Now we need to know what is a quantum computing. In very simple words, it's a computing paradigm that exploits quantum mechanical properties. What are these properties? Superposition, entanglement, interference, and decoherence. We'll talk about them. Of matter in order to do calculations. So it's a simple computer, what computer does, but it uses the properties which are very different and defies our logics of physics and understandings our surrounding. So it comes from the physics. It's evolution of physics turning into a technology. So let's talk about these four first: superposition, entanglement, interference, and decoherence. The quantum superposition. So see, in classical computers, we have 0 and 1. So there could be, it's like a switch. You can either turn it on or turn it off. But in quantum computers, it's something called qubit, quantum bit, which is turned on and turned off at the same time until you observe it. It is in both state. For example, coin flip. If we flip a coin, it's continuously rotating at the infinite speed. We don't know whether we'll get tail or head until we stop it. So it's very simple. You can put two information in a single coin, 0 and 1, because you don't know yet until you observe it. Otherwise, in earlier, what you used to do, you need to do two qubits, 0 or 1, to find a one state. So you want switch on, then there will be off condition, and there will be an on condition, and you will have to pick one. But in quantum computers, you can put two data in 1 bits. So every time you increase the number of bits, you will have 2 times the number of information that you can share. So it's again like example of switch. There could be a possibility when you turn off a switch, the switch doesn't go directly turn off. It starts decreasing the intensity of light. So there are infinite possibility. You can put the switch in between turn on and turn off. It's like that. That is called superposition. Power of being in a multiple state at the same time until you observe it. Why it is useful? You can, as I mentioned, you can put more information in a single bit. For example, you will hear about the bits, number of bits in a quantum computers has achieved. You will hear the lots of computers, Google by Google by IBM, that they have developed 30 qubit computer, 40 qubit computers. That's what they mean. So every time you increase the number of bit by n number, the number of information that you can share will be increased by 2 to the power n. For example, in 30 qubit computer, you can already store, in just 30 qubit computer, you can store 1 billion states. In 50 qubits, it's 1 quadrillion states. And in 300 qubits computer, which we're trying to create recently, the Liberty American company has come from that, claimed that, but there's a different problem. We'll talk about that. 300 qubit computer can hold more information than all the atoms in the observable universe. So that is the scale of quantum computers that gives you the power of calculation and power to save information. Now see, these are the development of the computers since 1998 to most recently the company called Rigetti is trying to build they have claimed, in fact, that they have built a quantum computer with 1,000,000 qubits. But this is not as simple as it sounds, and no need to trigger by these numbers 50 qubits, 72 qubits, because there's a problem called quantum decoherence. We'll read about this again, which suggests that the number does not mean much if you can't manage and keep them stable and then do calculations. They are very fragile states. So this is the development by different companies. So you can understand when you hear about this company creating quantum computers of a particular bit, what they mean. Now, the second most interesting and intriguing property is entanglement. So it's two quantum particles connected in a way that cannot be explained, that has not been explained yet. But when you change the characteristics of one state, the other one automatically changes, no matter how far they are. So two entangled electron, one you keep on Earth and another, for example, in Mars. And when you flip the state of one qubit, one electron, the other one at the Mars will automatically and instantaneously switch. How does it do that? We don't have any explanation, physical explanation, scientific explanation for that. You can give the example. If you read the example, the magical dice, you change the dice and then the other one automatically flips. That is how they are entangled. Why this is powerful? Because you can, for example, a 10 pair of qubits divided across the people. If I flip here these 10, the other ones, no matter how far they are in US or somewhere, they will automatically flip. So you can share the information without any cross linkage. So it's like a perfectly perfect way to communicate without a chance of leakage of anything at all. That's the power of physics that's coming to this technology now. We'll read about quantum key distribution that works on this exact principle. The phenomena of entanglement, the way it is transferred is so so fascinating that there's the term they use for the information transformation is quantum teleportation. So it's getting vanished from one place and coming out somewhere else. Albert Einstein called it in the beginning spooky action at a distance because he could not understand it. But him being Einstein, he tried to solve this equation, find out how this works, and he came with a solution, thinking that he's Albert Einstein, so people would believe him. But after decades of experiments, scientists find out that he was right. We don't know. So, decades of scientific experiment to just find out that we don't know this. it's still the spooky action at a distance, like Einstein said in the beginning. Third one is quantum interference. Uh, Rather the content, I would like to show you this picture. The waves by throwing two stones in a pond generate waves which interfere with each other. So either they can counter each other and destroy the entire wavefront, just like the constructive interference. Two waves lying onto each other perfectly aligned, they will result in a bigger wave. But if they are little off, the top point of the one wave is hitting the bottom point of the another, they will destruct each other and you won't have any output. So this is the probability interference. So in quantum domain, we calculate probabilities. Okay, we don't know exact solution. We calculate probabilities of finding an exact solution. So lots of probability waves. One point the probability will be high, next point it will be low, then high, then low. So this is a wave, lots of waves. Now they wave interact with each other, and sometimes they constructive, they create a bigger wave. Sometimes they're destructive. So sometimes they create nothing at all. So what we try to do is why we try to start these waves in such a way that we only get constructive interference. So there will be larger waves. That means we are moving towards a solution, and we try to avoid destructive interference. So that is just the try the idea. No need to get into the detail. It's a mathematical explanation only. It goes into the probability calculation, and then how it's just a intuitive way to understand it. Third is no cloning theorem. Very simple. You can't clone, or you can't decode quantum state going from one place to another, because it's essentially qubits. If you try to observe that, their state will change. As I mentioned, until you observe it, it's decoded. It's not decoded, it's coded. So you can transfer information from one point to another. If somebody tries to eavesdrop and try to figure out your communication, what's going on, they will have to observe it. Once they observe it, the entire state will collapse and they won't get anything. That is just no cloning theorem. You can't clone a quantum state. You can't interfere in between. You can't eavesdrop in between. That is how the quantum cryptography works, and which is the unbreakable, physically unbreakable method of communication. Quantum decoherence. Now this is called the enemy of quantum computers. Quantum states are very fragile. I said lots of qubits in a computer, but you can't have them more than a fraction of second. But you need to do calculation in that fraction of second. So they are very fragile. They are made to stable in at the ultra cold temperature that around the 0 Kelvin. It's the coldest temperature the humans can achieve. Physical limits of the temperature that we can go down. We have to keep the quantum states, the electrons, at that temperature so they don't vibrate. Until electrons have energy, they will keep vibrating. So we need them stable. So we will leave all the energy from around them. That means taking to the absolute cold temperature, they won't have any energy. Then we'll hit a laser on them and their state will change. That's how we control them in quantum computers, suppose. So these are the technologies. No need to put emphasis on it. What you need to remember is the type of technology used by the company. For example, the superconducting loops are currently being supported by Google, IBM, and quantum circuits. Similar, the trapped ion technology is being used by a company called IonQ. It's a very famous company. They have claimed quantum advantage. I will talk about that. Similarly, like Google. Third one is silicon quantum dots. It's used by Intel. They are being developed in a very theoretical manner. Microsoft and Bell Labs is using this topological qubits technology, which is at very theoretical level. They have not been able to achieve, but it shows great potential theoretically. So they are trying to stick to that. Third one is diamond frequencies. It is being developed by quantum diamond technologies. In India, we are using the first one. The one Ion Pi Q, the private sector company startup that is trying to build a quantum computer with the government support. It's using a supercomputer conducting loop. So you just have to remember that. You can see the longevity, the seconds it survives. So 0.00005 seconds. This state survives. The qubit survives for that long only. For some, it's higher, but then you can't keep them for, you have extremely high technological barriers to bring that. You don't have the technology. Now, important terms that you will get to hear about this technology is quantum gate. It's similar to computer gates, AND gate, NOR gate. You heard about the logical gates in a computer. They are just the ways gates where the information is passed and changed after that. So in quantum computers, the same gates are quantum gates circuits. The same circuits in our telephone, TV, and everywhere. In quantum computers, these circuits are called quantum circuits. The algorithms we talk about in AI and everything, the algorithms which are used in quantum computers are called quantum algorithms. Examples are Shor's algorithms, Grover's algorithms. We'll talk about them. Quantum processing units, just like in computers, CPU is there. In quantum computers, it's QPU. This is the image of the QPU. This is the purest form the gold humanity can create. This has to be the perfect 100% pure gold in order to perform the functions we need to do. So that is QPU. Then superposition, we have learned entanglement, decoherence, no cloning, interference, all these. Now coming to the technology part, there are 4 verticals of the quantum technologies. Quantum computing, where we solve the problems, mathematical problems, and figure out a solution. Then quantum sensing, the sensors that we use, they are developed on quantum technologies, very ultra precise, very accurate, unimaginably accurate. We'll talk about quantum communication. I mentioned it's unbreakable. We cannot decipher, we cannot clone them, we cannot eavesdrop. Quantum simulation is something we can simulate the quantum properties of a material, like I mentioned, the caffeine molecule on a quantum computers. Huge application. We don't have to go into deep at this point. Now, the 3 terms that are being talked about most are quantum advantage, quantum supremacy, and QDay, the title of this lecture. Quantum advantage, very simple. The day when we find a practical application of quantum computers in a real world, the day when some company, some quantum computer achieve that company can claim that they have quantum advantage. Similarly, the day when quantum computers can perform a calculation, not practical, theoretical calculation, which is impossible by the most powerful supercomputer right now, then we will have achieved quantum supremacy. QDay is simply when the quantum computers will be powerful enough to crack the currently used encryption, which is RSA and RSA, mostly AES. These are the encryption that we use currently to decrypt information, like we use in WhatsApp, Meta and everything. The everyday communication that we hold on our computers and classical devices. The day when quantum computers can do that, there won't be anything secret, and that day is right now called as QDay. We are far away from that. It's not a day, it's a phenomena. We need to understand that. These are the terms you will hear when we talk about quantum day. Is QKD, quantum key distribution. It's a method of communication I mentioned in the physics, in the entanglement part. PQC, post quantum cryptography, the method that we can use right now to secure our data from quantum breaches in the future. MLCAM, MLDSA, SLHDSA, these are the ways of PQC, post quantum cryptography, that we don't have. These are developed by National Institute of Standards and Technology by USA, and already the world is having dependency on these technologies over USA, because they have figured out, they have created a post quantum cryptography standards, and now they are giving it to whole world. Even we are, when we have our infrastructure, our critical infrastructure, trying to install PQC, we are dependent on them. So see, dependency is already there. So this is the time we need to work on these technologies and be indigenized, because everyone is almost at the same stage. A little bit ahead, US and China, but not that much, we can't reach. Now, future of warfare within quantum technologies. In the 4 verticals that I talked about, in quantum computers, there will be calculations of the huge amount that we have in military domain, logistics, inventory management, optimization, troops, and everything. that can be done on this computer with perfect accuracy. We can have infinite number of possibility to win a war, and when we put all those possibility as the dynamic criteria, and we can have a proper perfect solution to win a war. There was a discussion by that again the Friedman, how this technology will be used in the future. So if being a weak country, for example, Nepal is being attacked by China, India, and let's say Pakistan all together, you would think that it's impossible that Nepal can win. But out of the billion possibilities, there would be a one single possibility that Nepal maybe can survive, can found a place where it can claim victory. Just Iran did against USA. Who would have thought? That probability out of those billions can be calculated by quantum computers of a 300 for say 400 qubits, perfectly functioning, no decoherence, no problems at all. That can be calculated. That is the power. We are, I mean, the humanity itself is far behind that, but we are getting there. Quantum communication, we can have a secure communication, very critical for military establishments. Quantum simulation, this is very important and most interesting thing, because we can have a whole new world with new drugs for working exactly, you know uh, you know the thing that you hear in the movies, that human are living for the hundreds of years, thousands of years. No disease can be uncurable. That can be achieved with a perfectly simulated molecules, how they interact inside our body through quantum simulations. New materials we can discover, energy technologies, how the batteries can perform better, how the quantum fusion that we are trying to can perform better. The technologies can be evolved in that manner using this simulation. That is the power they have. Together, these all four verticals can, in a terms of a kill chain that I feel quite interested about. That is quantum sensing. Similarly, simply to detect the target, perfectly made sensors. There will be absolute transparency on battlefield. Then quantum communication, perfectly encrypted quantum communication that cannot be break. Then quantum computing, perfect solution to your planning, and then execution. You will have a proper kill chain, proper way to winning a war if you have these technologies. In strategic terms, quantum technology could therefore contribute to information superiority, decision superiority, and ultimately decision to action advantage. The ultimate power to win a war using technologies that can be given by this technology. If you have that, if you have it first, that's the point. Now the quantum efforts worldwide, as you can see, in India, the 60 billion 735 million amount is the amount sanctioned by National Quantum Mission in 2022 February, 6,000 crores. That is the only investment until now. But you can see in comparison, China is spending 15 billion on this technology. United Kingdom 3.5. Even Canada has far more investment than us. France, Switzerland, US, global.
India, 60 million to 735 millions.
So 60 billion.
60 billion rupees, yes, sir. And then they converted into dollars.
6,000 crores, the amount sanctioned for the National Quantum Mission. We need to have a comparative understanding of how far we are and what other countries are doing. Russia, you can see, they have recently launched another program, still in a war. They have committed $5 billion again on this technology in the middle of the war. It's just like news of March 2025. This is our development so far. We used to think that our development in quantum technology started with the National Quantum Mission, but in 2018, we had the Department of Science and Technologies, a group of people from all over India coming together to start working on some sort of policy. We are late already, but we figured out, it's very interesting to see that government of India is thinking ahead with this National Quantum Mission, putting a huge budget dedicated to a single technology, which is, still in a theoretical domain, trying to get into the, technological domain. But the efforts has been are quite satisfactory to me as I can see. But there's a lot of need still to, because what we are trying to do through these startups and everything, we are trying to bring these technologies from other countries. We are not doing our own R&D. We're trying to replicate what they are doing it. We are trying to learn through IBM and all those. But see, this technology is coming from the physics that is there available to everyone. You know, the same Feynman lectures that were used by MIT scientists to develop their first quantum computer of 3 bits, it's available on YouTube. I mean, you can learn physics, you can learn about technologies, how you can cool down a particular element to the sub-zero temperatures, and then make qubit stable, and then do calculations. It's there. You need to put money, and you need to put best brains. The two things that you need to gain superiority in any technology. So that is what we're trying to achieve. That what is needed is the government, university, and industry need to bring money and brain on a single platform in a mission mode to find a proper solution, to start ahead, because it's not like a race that some country will build and have a quantum advantage and then others country will follow. If that is achieved by one country, the game is over. They won't let any other. It's a very simple game. Once you properly understand the quantum advantage, the power of quantum computers, like I mentioned, radars and everything, you will realize that having quantum advantage by one country ends the game. That will be the ultimate superpower for the eternity. It's the extreme of computers. There won't be another evolution of computer after quantum computers, because you are playing at the electron level. There's no other particle smaller than electron with a charge. So there you have reached the ultimate barrier of physics and turned it to a technology, and you need to get that technology before any other country does. The other things that I should have covered, but because of lack of time, that now you can understand, you can cover and explore our National Quantum Mission, what is all given in that, Indian startups and private sector in quantum technology, China's quantum progress. They are very secret about it. There's very little information about quantum progress in China, but here and there you hear some kind of claims that they have developed a quantum radar recently. Like in 2023, there was a news that China tested its quantum radar, and the power of that radar is that 3,000 kilometers from the radar, even a fly, an insect trying to take a flight now, they will know that there's an insect, the frequency of its wing flap, the size, and the height it has reached. That is the power of quantum radars. US has also tried to flex that. The recent Iran operation, there was a quantum ghost murder. There was a technology used where they found their soldier hidden in the, there was a crash and the soldier was in the Iranian territory, and they using a quantum magnetometry, it's a sensor, they find out the heartbeat of that soldier in a cave, and then find that soldier out and then took it out. It's all a story, mostly debunked by their own media houses. But see, the narrative trying to build is already that we have this technology, we achieved certain level of proficiency, that we can do this. Because once you are actually able to do that, it's the end of the game. With that, I would like to conclude my lecture.